This video is another in our series on doing things with geometric algebra, and in it we will solve a problem that was suggested to us by Professor Francisco Montoya, who is a member of our associated group in LinkedIn, Pre-University Geometric Algebra, and I'll present the link for that group in the video description. And the problem that Professor Montoya suggested to us is the traditional Snellius-Pothenot problem, in which a person who is at an unknown location P is trying to establish his location by taking sightings of three known points A, B, and C. And from this person's position, the angle that subtends the segment AB has a measure alpha, and the angle that subtends the segment BC has the measure beta. In this video, what we will do is first of all formulate the problem in terms that will allow us to use geometric algebra. Then we will solve the problem and transform the solution in a way that will allow us to check the solution via the program GeoGebra, which is what I use to prepare this video. And I will be linking resources that we use either in the upper right hand corner or in the video description. So let's go ahead and formulate this problem first of all in a way that will allow us to use geometric algebra. So what we have done is we have our points A, B, and C, the three known points. We've defined the vectors A and C and the vector from B, the known point B, to P. This is our vector here is P, and we have our angles alpha and beta. The other thing we've done here is we've defined the sense of rotation of our unit bivector of this plane. So I tried various ways of solving this problem, and the ways I had tried did not work very well. So what I did then was I considered just the other points in the plane from which the angle that subtends chord AB is also alpha. So all of those points in this plane from which the angle that subtends that chord measures alpha lie along a circle, and P is one of those points. So let's show that circle. Now, using some ideas that I'll present or that I'll link up in the upper right hand corner here, we can determine the radius and also the center of this circle. And the vector from the known position B, or the known point B, to that center is A over 2, so it's half the vector from A to B, plus a scalar multiple of a 90-degree rotation of A, and that is this part. So that's how we find the center of that circle. Similar comments apply to the angle beta. All of the points from which the angle that subtends the segment BC measures beta also lie along another circle here. And I'll get rid of this angle over here and show this other circle. P is one of those points as well, and we see that the 2 points of intersection of these two circles are in fact B and P. So how can we make use of that? Well, to get an idea, let's draw the line that joins the centers of these two circles. And if we do that from our knowledge of geometry, our previous knowledge, we know that the vector from B to P is perpendicular to the vector that joins the centers of these two circles. So from that, what can we do? Well, in geometric algebra terms, we would say that first of all, B and P occupy positions that are symmetric to each other with respect to this vector, or with respect to this line, to be more accurate. So in geometric algebra terms, the vector from B to P is equal to twice the rejection of the vector MA with respect to the vector MC minus MA. So how can we formulate that in geometric algebra terms? Well, it's quite a standard thing to do. The rejection of MA with respect to MC minus MA is the outer product of MA with this vector MC minus MA times the multiplicative inverse of MC minus MA. And now, because the outer product is, or has the distributive property, MA wedged with MC minus MA, well, is MA wedge MC minus MA wedge MA. And the outer product or wedge product of any vector with itself is 0. So this simplifies to 2 times MA wedge MC times the multiplicative inverse of MC minus MA. So before we proceed to transform that, let's recall that the multiplicative inverse of a vector is simply the vector itself divided by the square of that vector's norm. And also, any outer product is a scalar multiple of the unit bivector of that plane that contains the 2 vectors. So let's go ahead and do our transformation. So what have we done here? Well, the first thing that we've done is recognize that MA wedged with MC is some scalar multiple, in fact the norm of that bivector, times the unit bivector for the plane. The next thing we've done here is the multiplicative inverse of MC minus MA is again MC minus MA itself divided by the square of the norm of that same vector. But instead of putting the square of the norm here, I've distributed that square as the norm in this denominator here times the norm of that same vector here. So what is MC minus MA divided by its norm? Well, it's the unit bivector, or the unit vector I should say, in the direction MC minus MA. And what we now have here is a scalar multiple of the unit bivector I. But when we multiply a scalar multiple of the bivector, of the unit bivector, times a vector within that same plane, what we get is a scalar multiple of the 90-degree rotation of this vector here. So our answer now, P is expressed as 2 times a scalar multiple of the 90-degree rotation of the unit bivector of MC minus MA. And the minus sign here, well, to establish whether it's a plus or a minus, that we have to think about a little bit when we do this transformation, but I'll leave that aside for the moment. So again, the main thing that we have here is that P is a scalar multiple of the 90-degree rotation of the unit bivector, or the unit vector in the direction MC minus MA. So let's see how we make use of that fact, or of that representation, in order to check our calculation by using GeoGebra. Here's the command that we use, or that I used at least, and we have to note that in order to use this, or this command applies only when our reference point B is at the origin of the plane. So I'll leave this aside here exactly what's going on, but what we have here is, first of all, taking the easy part, the rotation that is effected by I is implemented by the command rotate by 90 degrees of the unit vector of the unit vector of the vector VECTmC, which is that, minus vector MA. So this part here is the rotation of this unit vector. So what's going on here? Well, the norm of MA wedge MC is accomplished by the absolute value of the cross product of MA and MC. Why the cross product? Well, the cross product is available in GeoGebra, but the wedge product is not. But the thing about the cross product is that it is equal in magnitude and in algebraic sign to the wedge product of these two vectors. So I can just use this cross product here, or its value in algebraic sign, in this scalar multiple here. And of course the norm of MC minus MA is just in GeoGebra. We use the absolute value of that. So that is how we can use GeoGebra to calculate, to check our solution without having to go through the mess of using coordinates. I hope that this video has been useful, and I look forward to your comments. And again, I do hope that you'll consider joining the LinkedIn group Pre-University Geometric Algebra, and I'll put the link for that group in the video description. Thank you for your time.